Hi everyone, welcome to the final session of today's Quantum Tech presentations. I'm delighted to have with me Andy Edmonds, who's Principal Scientist and part of the R&D team at Element 6's Global Innovation Centre in Harwell. That's in the UK. He's over 15 years of experience of diamond defect physics and synthesis across both academia and industry. He joined Element 6 in 2013 and is currently working on projects focusing on optimization of CVD diamond synthesis for quantum sensing applications and the further development of characterisation techniques. So with that, Andy, I'll hand the floor over to you. Thank you.
Okay, hello everybody, and thank you, Amit, for the very kind introduction. So, as previously introduced, my name's Andrew Edmonds from Element 6, and what I'm going to do today with you is give you a flavour of some of the work that myself and my colleagues, who I list here, some of the work that we've been doing over the last few years to really transform diamond into an engineered solution for, given the topic today, quantum sensing technologies. And I want to thank also the previous speakers in the sessions today for their very interesting talks. So I'm conscious at the beginning of this talk that some of you might not know who Element 6 are as a company and what we are about. So we actually have a long history as part of the De Beers group of companies, and we date back all the way to 1946. So we've now been involved in diamond innovation for over 70 years. So essentially we take the unique properties of diamond and other supermaterials and try and deliver engineered solutions to a wide range of applications. And these applications are broadly spread across two different themes. Firstly, we have the abrasive applications of diamond, which simply look to use the hardness of the material. And in these applications, we're essentially using cutting, drilling, grinding, or polishing applications, exploiting diamond's intrinsic hardness. And then we have what we refer to as the technological applications, which essentially look to use the properties of diamond that extend beyond simply the hardness of the material. So traditionally, one of our big application areas within technologies has actually been in optical. So what I have here is an optical window made of diamond. You're going to have to trust me that it's diamond and not a piece of glass, but the key difference with diamond is that we have an optical transmission window in the case of diamond that extends from the UV into the far infrared. So that, when you combine it with the fact that diamond has a very good thermal conductivity, means diamond is an excellent material for modern high power infrared lasers. But given the topic today, obviously I'm going to be focusing on the emerging quantum applications using lab-grown diamond. So one of the reasons why diamond has become such a big part of emerging quantum sensing technologies is because of a particular defect or color center that we can find within special diamonds. And this is the nitrogen-vacancy center, or for short NV center. Now, throughout the last few decades, there's been an awful lot of really beautiful experimental and theoretical work to really understand, to begin with, this defect, and then more and more in increasing years actually utilizing the properties of this defect. Now, I don't need to go into too much depth on the beautiful spin physics of this defect, but there are a few key points that I want to emphasize. So if we have this defect in the negative charge state, we have a spin of 1. Now, when we look at the spin state structure of this defect, we can spin polarize the ground state, i.e. create these defects in particular levels in the ground state by simply optically pumping this system with a green LED or laser. One of the other critical factors of the NV center is we can actually encode which spin state we live in, or read out the spin state that a particular defect is in, by measuring the amount of luminescence that this particular defect gives off. Essentially, we see a difference depending on whether it's in one of the plus or minus 1 spin states or the zero spin state in the ground state. So we can optically read out the spin of the defect. So what this means is we have an all optical scheme of initializing and reading out this spin state. Furthermore, in the ground state, we can manipulate which spin state a defect lives in with microwaves. And the magic of the MV center in diamond is all of this is possible at room temperature. And because of the strong tetrahedral bonding structure of diamond, we intrinsically, in pure diamond samples, obtain a long coherence time. Now, one of the reasons why this particularly gained attention in the late 1990s was that people found with very, very back then rare diamond samples, you could actually perform fundamental experiments on single NV centers. So it's like having a single atom system at your disposal, but enclosed within a nice, stable, solid state material. But back then, as I mentioned, those samples were relatively rare. What was really needed for this community to grow further was a source of this material on demand. Now, Element 6 has been working in the technologies of synthesizing diamond in the lab for decades. And our main technique that we use in this space is chemical vapor deposition, or CVD. Now, CVD, as the name suggests, involves a chemical reaction that occurs in the vapor phase above a substrate that causes deposition onto that surface. Now, when we look at growing the best single crystal diamond, and there's an example video that I'm highlighting here in the bottom left-hand corner of this slide, our substrate itself is a diamond substrate, and we are adding into the reactor a carbon source, which is typically methane, and hydrogen. Now, these molecules are dissociated by, in our case, a microwave plasma that sits within a custom designed reactor. Now, hydrogen is a critical part of this process because it etches away non-diamond phases as this diamond is growing up layer by layer. And there's a lot of levers at our disposal when we can optimize a CVD growth process. We can change the temperature of the growing diamond, the surface of that growing diamond. We can change the power in the reactor, the pressure. All these things we have to concern ourselves with when we're trying to generate a specific grade of diamond material. Now, one of the headline results from our work was back in 2002 when we synthesized the first, what we refer to as electronic grade diamond by this method. Now, what this essentially means is the purity of this material is less than 5 parts per billion nitrogens. That means you need billions and billions of carbon atoms before you will find one impurity atom. So this is much, much purer than you'll find in nature, apart from in freak samples. And it's interesting to note that actually some of the early experiments that went on with MV centers in diamond were actually performed on a natural diamond, but it was so rare that it was referred to as the magic Russian diamond. And I would encourage anybody interested in learning more about that to Google the term magic Russian diamond and watch a really nice YouTube video that's been put together on that subject. So this material we made commercially available in 2007. And really what I want to emphasize in the next few slides is how the emergence of this material was really crucial in the wider studying of this system and ultimately the quantum diamond research that is now going on. So if we backtrack slightly and think about what we've made with electronic grade diamond, we can start thinking about what that means in terms of how many MV centers somebody might find in this material. So as a typical rule of thumb, for a range of nitrogen CVD material, we typically observe a ratio of substitutional nitrogen defects to the negative MV defect, which is the defect and charge state that we're interested in, the ratio of around 300 to 1. So if we recall, we said that concentration in electronic grade diamond is typically around 1 part per billion. So what this means is in the volume of 10 by 10 by 5 microns, we would only expect about 30 at most negative MV centers. So what this means is if we have at our disposal a confocal microscope, we can search around a bit and fairly readily find single isolated negative MV centers. So instead of having to find a rare diamond sample, you can then instead go and buy a sample where you can find these isolated MV centers. So what I show here is the map over time of just how the number of academic groups and industrial people interested in this technology has really emerged over the last few years. And I actually need to update it because it stops at 2017. But the other way that we can look at it is by simply the number of papers, journal articles there are in this space per year as a function of time. And what's again quite noticeable is where our development of electronic grade fits into this story. And really, this was crucial to supporting this explosion of interest in this system in diamond. So we've really supported this sector in two ways. Firstly, by making this diamond material available for the early researchers. And also, we ourselves have been involved in a lot of collaborative quantum-related projects, again, since around 2007. So what we've talked about so far are essentially MV centers that we find that are accidentally incorporated in high purity diamond, but we might instead, depending on the application, want to produce increased levels of MV in our material. And really the approach that we use depends on how much nitrogen we have in that starting material. So if we have a high purity material, such as electronic grade that I've previously introduced, we can use nitrogen implantation to increase the amount of nitrogen in that material. So essentially we can implant single, if we want to, nitrogen atoms into that substrate. Now the process of implantation also leads to vacancy production, essentially a little bit of damage around that nitrogen atom that we've implanted. We can then thermally anneal the diamond at temperatures above which vacancies are mobile, which is typically above around 800 degrees C, and the vacancies will find a nearby nitrogen atom and form the MV that we're after. So with this technology, we can form MVs at chosen locations, but the MVs are only found close to the surface. Ultimately, an implanted nitrogen atom can only penetrate so deeply into a diamond substrate. So that's the low nitrogen case. If instead we want to create higher concentrations of MV that exists throughout the bulk of a diamond sample, we can take advantage of the ability within CVD to actually deliberately add back in a controlled amount of nitrogen into the process. Then again, as before, we can use electron irradiation to produce vacancies, thermally anneal to produce MV, and through this method, we can produce, if we want to, high concentrations of MV that exist throughout the sample, or alternatively, we can grow high nitrogen layers on top of a high purity substrate and then have comparatively thin homogeneous layers of MV in an otherwise high purity sample. So the early work that I discussed back then concerning single MV centers was really concerned with fields such as quantum computation, the generation of single photon sources, etc. But what's really emerged over the last few years is that there are also other quantum-based applications of diamond that are more around the sensing domain. So one example, the main example I'm going to focus on today, is the idea of using MVs in diamond to measure a magnetic field. And we can do this by this schematic that I show on the top left-hand side of this slide, using the electronic Zeeman interaction. So our plus and minus 1 spin levels in the ground state are split by the presence of a magnetic field that is along the MV axis of this particular MV defect. So then through the electronic Zeeman interaction, we observe a splitting in energy levels that is proportional to the magnitude of the magnetic field along that MV's symmetry axis. And then using the principles that we've described before, we can understand that this experiment is actually relatively simple. All we have to do is scan the microwave frequency that we're applying to this system, measure the amount of light that's emitted by the diamond when we're pumping it with a green source, observe for a single MV case, the two resonance lines that we see in terms of a dip in luminescence, measure that splitting, and then we have a direct calibration-free way of measuring the magnetic field that is along that axis. Now, if instead of a single MV center, we think of an array of MV centers that are populating not just the one orientation that I illustrate in the schematic here, but the other four possible orientations, we will observe a larger number of resonance lines corresponding to the magnetic field projected along all those different axes. So what we have at our disposal is actually a vector magnetometer that's all encapsulated within one diamond sample. So very powerful. And then what I show at the top here is really just making the point that to illustrate this effect is relatively simple in terms of the equipment that you need. You just need an intense source of green light, an LED or a laser, that you focus onto a diamond sample containing an ensemble of MV centers. We typically apply a known static magnetic field just to remove this initial degeneracy in the spin levels, so we can then measure small splittings on top of a known splitting. We need our microwave coil to deliver the microwave radiation, a filter to remove the green light, and then simply a photodetector to measure the amount of red light that is emitted. So what this means is that we and other companies have been able to put together very simple demonstration units with essentially commercial off-the-shelf components out of obviously a nicely engineered diamond sample that illustrates this effect. And we found this as a really powerful tool. It's much more impactful when we demonstrate this technology to a customer, when we can actually show them a box that is demonstrating the principle rather than directing them to a list of academic papers. So from our side of things at Element 6, what we really need to be concerned with is what we can do with the material to really optimize the sensitivity, say, of a magnetic field sensor. And our primary concern is obviously looking at the properties of the material itself that can influence the sensitivity. So what I show at the top right-hand corner of this slide is the fundamental equation that tells you the minimum magnetic field that you can detect with an MV-based sensor. And what I've done here is pick out the key material-related terms that we're concerned with. So the first one, the most simple one, is simply the number of MVs that we're using in this system. If we have a larger number of MVs that we use, so a larger ensemble of MVs, we'll observe more luminescence and a signal is more readily detected. The coherence time is also critical because what we've seen in this schematic shown again in the center of this slide is this idea that we see two or groups of resonance lines, and it's the sharpness of these resonance lines that's given by the coherence time. So a sharper resonance line makes it easier for us to detect a small change in magnetic field, so a more sensitive device. And then there's the concept of contrast in this device. Now, it's important to remember that all the spin physics that we've discussed only works if our MV center is negatively charged. In reality, in the diamond sample, we'll observe both negatively charged, which is this spectrum I show in the bottom right in red, and neutrally charged MV sensors, which is the spectrum I show in blue. These spectra overlap. So essentially, if we don't engineer the diamond to contain a high fraction of MV minus compared to MV neutral, the MV neutral has the potential to swamp the emission spectrum and erode the contrast that we're trying to measure in performing the measurement of magnetic field. So in practice, what this means when we produce a diamond sample for this sort of application, we need to concern ourselves with a whole host of material-related factors, such as the things that can fundamentally affect the coherence time, T2 star, which are things like the nitrogen that we've added into the material, and the amount of other paramagnetic defects that can exist in that material. And we also have fundamental things like the size and shape of the diamond sample, which can influence how easy it is for us to inject the light into the diamond sample and then conversely collect the luminescence that we're interested in. The other fundamental question that we need to answer when we think about growing a diamond for this sort of application is how much MV do we want in this material? And really, there's different approaches that exist when optimizing the number of MV centers used by a sensor. Firstly, we can increase the number of MV centers simply by increasing the area, so increasing the size of the piece of diamond that we're using at a fixed MV minus concentration. Or alternatively, we can increase the MV minus concentration and keep the volume fixed, or obviously a combination of those two things. Now, these two different approaches are illustrated in this paper from Cleverson, where in the case of a low MV containing diamond, one potentially optimal scheme is to inject a laser into a facet along the side of the diamond sample and then let that laser bounce around multiple times within the diamond sample using total internal reflection. Now, this only works in the case where we have a low concentration of MV minus, because in the high concentration case, the MV itself will start to absorb the laser that we're using to excite the luminescence. So if instead we think about a high MV containing sample, it's more typical just to focus a laser or an LED in a small volume of that sample in what's referred to just simply as a single pass arrangement. Now, there are advantages and disadvantages of these two approaches. And one of the downsides potentially with the low MV case is that you have the challenge of increasing the active area of your sensor. What that means is you need a homogeneous RF and bias magnetic field across the volume that you're using. The other critical thing that I need to get across is this idea that the coherence time is related and dependent on the amount of nitrogen that is present in the material and also the amount of carbon-13. Now, carbon-13 has a nuclear spin, so it also acts to dephase MV centers. And this is the plot that has been lurking on the right-hand side of this slide. This shows the dependence between nitrogen and the coherence time with different abundances of carbon-13. Now, we can use this to pick out areas of interest in terms of developing a MV containing diamond material. Now, in the single MV case for electronic grade or ELCVD, we obviously sit here in terms of nitrogen concentration. What I'm going to focus on are two target levels of nitrogen in the material that we've been developing. One exists around 1 part per million nitrogen, which is a logical concentration to choose because in the natural abundance case, this is the maximum concentration that we can use before this coherence time starts to drop off. And then the other target that I'll focus on is around 10 ppm of nitrogen, where again, it's reasonably favorable in natural abundance, but we can start looking at whether there's other ways of us recovering the coherence time that we've otherwise lost by increasing the nitrogen concentration. So before going into the details on the material development that we've been undergoing, I just want to give you a flavor of the breadth of applications that MV and diamond touches. And I'm happy to share this slide to anybody who's interested because it nicely lists all the papers that display these fundamental demonstrations. Now, later on, I'm going to give a couple of case studies on bulk magnetometry, but at the moment, I just want to focus on a couple of other nice examples that I particularly like. So one is in the field of wide field magnetic magnetometry. So here, we're not only using the potentially high sensitivity of magnetic fields with MV centers, but we're also using the spatial resolution that an MV-based system can deliver. And this is a very nice paper from Roger Fu and collaborators at Harvard University, some of our collaborators, where they've taken a diamond-based MV microscope that they've developed with our material and imaged, believe it or not, meteorites. So really they're using this to probe the magnetic field signature of the early stages of our solar system. And what I'm illustrating in the top right here is the comparison between what you observe in this sample using a conventional squid that we've already heard a lot about in previous talks today, compared to their diamond-based MV wide field imaging system. And the difference is quite remarkable in terms of spatial resolution. Then the other emerging application that I think we'll hear more about in the years to come is this idea of a diamond-based maser, which is at the bottom of this slide. So this is the microwave equivalent of a laser, and this is work and experimental demonstrations that have been done by the group at Imperial College London. So again, this is an area that I think will be very active in development in the forthcoming years. So now I want to talk about the development work that we've been doing in terms of the material that we can deliver to the community and our industrial collaborators. So what we've been doing most recently is trying to develop products that we can sell to interested people that really repeats the paradigm of the early stages with electronic grade, i.e. start to introduce to market some diamond materials that contain higher concentrations of MV centers to take advantage of some of the possible applications that I've been discussing. So we're doing this by launching a number of diamond materials under the banner of the Diamond MV or DNV series. So again, the idea here is just really to increase the availability of this material. So Carl, early on in the keynote talk at the start of today's session, put it quite nicely in terms of this concept of a quantum supply chain. So what we're trying to do is really ensure that at the fundamental material level, the supply chain is more assured, and we can really nurture this emerging application area and seed the market, if you like. So as part of this, the first material that we've delivered under the DNV series was what we refer to as DNV B1. So this corresponds to a material that contains around 1 part per million nitrogen. We launched this back in June last year. Now this material has the properties that you would expect, given the plot that I presented on the previous slide in terms of coherence time. And you very readily, when exciting it with a green LED or laser, see red luminescence. So you very readily have a general purpose solution to really start doing some of these experiments and developing your own magnetic field or other sort of sensor with MV sensors in diamond. And this little video playing at the top right is an example of the red luminescence that you see in this grade of material when you pump it with a suitable green light source. So one of the things that we're particularly proud of in the team is that this material and this product was awarded the SPIE Prism Award in the field of quantum. So this has really encouraged us and given us some further reasons to increase the number of products that we've got within the DNV series and hopefully continue this story. So at the same time, as mentioned in the earlier slide, we've been working on higher nitrogen containing materials at around 10 parts per million. Now this is typically a really challenging area for people to grow nice diamond samples. And this is really because you need to control the presence of what I'm going to introduce as parasitic defects that can affect the coherence time and contrast. You also need to achieve reproducibility between the samples and control strain in the diamond material, which I'll explain shortly. And that's also detrimental to coherence time. So if we think about parasitic defects, it's most easy to introduce by illustrating what typically happens when you increase the amount of nitrogen in a CVD diamond sample. And this is what I show here. Instead of having a nice colorless diamond sample, what typically happens is the diamond becomes brown as we start to increase the amount of nitrogen present in this material. So this isn't because of the incorporation of nitrogen itself, it's by the presence of other, in some cases, nitrogen-related defects, such as the nitrogen-vacancy hydrogen center in this material, and also things like vacancy clusters that can form. It's a combination of these two things that erodes the optical properties of the material. Now, MVH minus, for example, is also paramagnetic. So very clearly the presence of these sort of defects can have a dephasing effect on the diamond and reduce the performance of the material. The other obvious point is that if a material becomes less optically transmissive in the optical, we're going to start absorbing some of the laser light that we're using to excite the luminescence, or potentially absorb the luminescence generated within the bulk of the diamond sample itself. So this is really critical to minimize if we can. We want to increase the amount of nitrogen in the material, but not at the expense of these sort of properties. And then I mentioned strain. So this is an example of what we see if we don't control strain in this sort of grade of material. What I show here is a optical birefringence image in the first instance, where we can see regions of high and low birefringence, which is a proxy to the strain in the material. Now, what we've done with our collaborators at Harvard is then map out what the coherence time is in different regions of this sample, and we can erode the coherence time very easily by a factor of 3. So this will have a majorly detrimental effect on the performance and sensitivity of this sort of piece of diamond for sensing applications. And in this particular example, the rough rule of thumb that we see is that birefringence in excess of 10 to the minus 5 has a significant effect on that coherence time T2 star in this particular type of material. So we need to clearly control that. So I don't need to dwell too much on the development process that we undergo. It's fairly self-explanatory, but essentially we would take our target specification for the diamond material. In this case, I'm talking about material with around 10 parts per billion nitrogen. We would grow bulk or sometimes thin layers of that material, process it to material that we can then very carefully characterize and then feed that back into the loop. And really, it's the characterization stage that is critical. We need to be measuring the right things and sometimes using proxy techniques that are faster than doing involved quantum tests in a sensor. But we need to do the right characterization to speed up this feedback loop. Now, once we're happy with that initial material, we can fix the recipe and start growing bulk samples that we can do further characterization or send to our collaborators for further study. So really in this study, what we focused on is 3 main properties and 3 main areas: increasing the nitrogen concentration, but whilst controlling the parasitic defects that I've been discussing. Obviously, crucially, reducing and controlling strain in these very high nitrogen concentration materials. And then, as I've remarked, really using characterization approaches that allow fast feedback of this process. So as part of this study, we commenced an initial exploration of all those levers that I explained earlier that we have at our disposal during the CVD growth process. And to begin with, we grew relatively thin layers of this material on moderately pure CVD substrates. Now, through that study, what we were able to do is find a range of conditions that actually allowed us to grow diamond containing higher nitrogen concentrations, whilst at the same time actually reducing the amount of parasitic defects that are present. That's what I illustrate in the center of this slide. We can see that actually as we move from left to right, our nitrogen concentration in the material goes up, but clearly the amount of discoloration of the sample, which we're using as a proxy to the content of parasitic, potentially paramagnetic defects, this goes down. So we produced a high nitrogen containing material that has a lower concentration of parasitic defects. This is exactly what we want and what we were after in terms of developing this sort of diamond material. So really the message here is that high nitrogen CVD doesn't necessarily lead to an increased level of parasitic defects. We can control that. So with that initial result at our disposal, we started looking at the reproducibility of this process and this particular recipe. So for this, we produced a batch of material and assessed the consistency of the critical nitrogen concentration prior to irradiation and annealing, which again is the process that we're going to use to transform this initially present substitutional nitrogen bath to MV centers. Now, what we found in this initial batch of samples is that we we had good control of the nitrogen concentration between samples, an average at around 13 parts per million, so pretty close to the level of 10 ppm that we were originally envisaging, with a very small scatter between samples. So it looked very positive. And the technique that we use to make these measurements is simply absorption spectroscopy, UV-vis absorption spectroscopy. And really, there's a wealth of information that we can get by this spectroscopic technique over and above just simply the amount of nitrogen. So it's really by probing this spectrum in further detail that we can gain a greater insight in exactly the purity of this material in terms of both nitrogen and parasitic defects. So clearly from these initial results, we had good control of nitrogen across a batch of material. But then what we had to be concerned with was, did we have good control of vacancies that we were dosing via electron irradiation that would ultimately give us a consistent MV concentration in the final material? So we looked at the control during electron irradiation. And to begin with, we simply mapped out the amount of GR1, as it's known, which is just an isolated vacancy defect in diamond, as a function of our irradiation dose. And this just corresponds to irradiating the diamond sample for a longer time. And in the case of increasing GR1 concentrations, what happens is our diamond becomes increasingly green. So we could then use this map to choose a suitable level of irradiation to create the desired level of MV centers in our material. And the second thing that we looked at was how reproducible the vacancy dose was. And we looked at this over a period of 12 months in different irradiation runs, and it varied by less than 4%. So again, the news is fairly good, we would expect, in terms of the reproducibility of this material. So from the last two slides, we have this combination of good properties in terms of small variation of the vacancy dose, which gives us control of the MV concentration. There's a small variation in the nitrogen content in this material. And ultimately, what this is important for is controlling the fraction of those MV centers that we've created that are negatively charged. We actually need some residual substitutional nitrogen in our diamond to donate an electron to turn MV from an otherwise neutral charge state to a negative charge state. So control and the small variation of substitutional nitrogen in the material will give us control of that charge state balance, which is the critical metric that we introduced earlier in terms of the contrast in the device. So then we can put all of that together and look at how reproducible the final MV concentration is in our diamond material. And that's the plot that I show on this slide, again looking at a batch of material. So we can look at the different charge states of MV and individually quantify those concentrations. And again, we see a very small variation in MV concentration between these samples. So reproducibility was good. So essentially the story from the last few slides is that through combined material irradiation and annealing control, we can produce material with MV concentrations and charge balances that are very reproducible between samples, which is ultimately what is needed when we start launching a new product to market. So I want to just briefly show you what these samples look like, because they're quite nice looking. One of the byproducts of improving and reducing the amount of parasitic defects is that we have a more vivid color, and this vivid purple color that you can see only comes about because of the few parts per million concentration of MV centers, and comparatively high concentration compared to what we were talking about at the start of this presentation, where we were literally just talking about one MV center. Is those MV centers that give that very characteristic and very pleasant purple color. So this is just a photo that I took of 6 example samples that are around 1 millimeter in thickness, around 3 to 4 millimeters laterally, from a batch of samples in excess of 30 that we produced. So we talked about strain earlier, so we need to start looking at the strain in this material clearly to get an idea of whether it will be highly performing or not. So what I show here again is optical birefringence images of this sort of diamond material. The good news is that the birefringence levels are at or below that critical 10⁻⁵ level that we identified earlier as being detrimental to the coherence time. So optical birefringence gives us an initial suggestion that this material would be very highly performing. But what is particularly nice is our collaborators, again at Harvard University, the Walsworth group, have actually developed new techniques to use the MV centers in diamond themselves to actually map out the strain and the shift in the resonance lines of the MV centers that's induced through the presence of strain. That's the map that I illustrate here. And the strain shifts that they found are well below the line width that you will observe for this sort of MV center concentration. So it's another way of saying that the presence and level of strain in this material is by no way at a level high enough to detrimentally affect the coherence time in this material. So hopefully the message that I've got across here is the developed synthesis methodologies have demonstrated low and controllable strain levels. So we can put all of that together now and start measuring the critical coherence time metrics for this material. We've done this by looking at both natural abundance in terms of carbon-13 isotopes, so that's 1.1% abundant, as well as special material that we've grown where we've deliberately depleted the level of carbon-13 present in that material. And then the Walsworth group have performed standard but recognized Ramsey technique measurements of this material. So what we found in the natural abundance case is that we see a coherence time of around 400 nanoseconds. This enables you to predict what you would expect the coherence time to be if you simply deplete the level of carbon-13 present in this material, but don't have any other sources of decoherence, such as parasitic defects or strain. And what you predict is a coherence time of 1.2 microseconds, which is remarkably close and pleasantly surprisingly close to what we observe in practice in measurement of this sort of material when we've depleted the concentration of carbon-13. So what we've demonstrated is that we can achieve coherence times that are then competitive with that 1 ppm recipe that we introduced earlier by depleting the levels of carbon-12 in what is otherwise a high concentration of MV centers. So in that sensitivity equation, we have this idea of the product of the MV concentration and T2 star affecting the sensitivity. And clearly in this sort of material, we have a very favorable product. So we would expect this to translate into a high sensitivity in practice. So I now, in the remaining time that I've got, want to focus on a couple of case studies where we've taken this sort of diamond material and worked closely with another company to hopefully develop diamond-based sensor technology in this area. Now, the first company that we've worked with is Lockheed Martin. Now, Lockheed Martin were interested a number of years ago because they'd identified the fact that MV centers in diamond are a potentially very disruptive technology in the field of magnetic field sensing. At the same time, at Element 6, we've been working in this space, as I remarked at the start, since 2007. So we've got a track record in this area. So a collaboration between Lockheed Martin and Element 6 made a lot of sense. Lockheed Martin is also the perfect company for us to work with because our expertise is mainly focused at the moment at the fundamental end of developing the material, developing some of the IP that goes alongside that. But a company such as Lockheed Martin bring a lot of expertise to the table in terms of the development and integration of a diamond sensor in a wider device. Now, initially, the application scope for this sort of project was quite wide, but the area that was particularly focused on in the end is denied GPS navigation, which was a topic that we heard earlier in this session from Ollie, and he explained the problem very nicely, so I don't need to go into too much depth here, in that GPS is not a inherently secure technology, and it's not a technology that you can rely on in all environments, even if you don't have a adversary who's actively trying to block the signal. So in this case, what we're potentially trying to do is to use the small local variations that exist in the Earth's magnetic field from location to location to augment other navigation technologies with this additional level of detail that is not reliant on GPS. And again, the critical thing here is that diamond MV based sensors deliver what is a true vector magnetometer solution compared to alternative approaches. It also has a very wide dynamic range, in addition to the advantages that we've heard about before in terms of being able to operate at room temperature. So you don't need bulky cryogenic equipment. So then ultimately, thanks to our diamond material that I've introduced, the high MV concentration material that we've developed, luckily we're able to develop a fully mobile magnetometer test platform, which has really taken this idea of quantum sensing in magnetic field sensing from the lab bench into the real world. And this is the device that they've put together and was also discussed in a nice article in Wired back at the end of 2018. So really the advantages here, as I've remarked, are the large dynamic range. Essentially, we can detect small changes in the magnetic field locally on top of the Earth's magnetic field without having to do any cancellation. And the sort of infrastructure and sensor they've built is designed to operate in a high shock and vibration environment. And through further development of this technology, there is definitely the potential to deliver low size, weight and power solutions. So it's a very exciting area of development. So in this endeavor, we've actually taken Element 6 as a company, what is for us a fairly unusual step of taking the lead on writing an academic paper discussing all these development efforts and the resulting diamond material. And the reason why we wanted to do this is to really get the message out there that diamond synthesis is now a mature technology. And again, the idea of this quantum supply chain, the material side is starting to become more assured. What we need as a community now is to build up the rest of the infrastructure around the diamond that's required to deliver a true sensing solution, whether that be in magnetic field sensing, RF sensing, temperature sensing, and all the other sensing modalities that were on the slide that I presented earlier. So through this paper, hopefully the message will permeate through the community that there has been an awful lot of development in recent history in this diamond material, and the diamond material is hopefully ready to support whatever ideas and whatever innovations can be generated outside of Element 6. And then very briefly, to give you an introduction on some of the other areas in magnetic field sensing, we're also working with a Canadian startup company called SBQuantum. Now, in the realm of mining, it's very common even now to use squids for tensor gradiometry to try and find suitable new sites for mining. However, as we've heard before, squid-based systems have a number of limitations. It's inherently bulky technology because you've got all this cryogenics that go alongside of it. And this is particularly difficult to handle in remote locations. So in the case of diamond magnetometers, we have exactly the same benefits that we've discussed on the last slide in terms of having that intrinsic vector capability when we have an ensemble of MV sensors. But the further information that you can get by building an MV sensor are things like the volume of material that you're dealing with, as well as the location. And ultimately, SBQuantum are looking to build diamond magnetometers into an array of sensors to perform tensor gradiometry to ultimately provide a richer data set. Now, for anyone interested in further information on this, we've put together a nice case study between us and SBQuantum that you can find on Element 6's website. So that brings me to the end of my presentation. So to summarize and conclude, what I've tried to get across today is that CVD diamond is a powerful and we think really uniquely suitable material for certain quantum technologies. And then quantum sensing applications, particularly magnetic field sensing, utilizing MV sensors in diamond, are reaching a mature level, and it's up to us to really ensure that the material is ready to support these endeavors. And hopefully that's what we've done, and that's what we've demonstrated today. Ultimately, I've focused on the development that we've put towards scalable bulk recipes targeting different levels of nitrogen, ultimately MV concentration, that are suitable for different device configurations that end users might have in mind. We've introduced a new CVD diamond grade, DNV B1, which was the first commercially available diamond quantum solution really to support this market. And ultimately, there exists a wide range of applications on the horizon, which we believe can really push the boundaries of existing quantum technology and hopefully unlock new markets and new possibilities for us all. So thank you very much for listening, and I'm happy to take any questions.
Thank you very much, Andrew. Fantastic presentation. I'm afraid we've run over a little bit. The platform will actually kick us off in a couple of minutes. We have time for just one question. A question from the audience. Where do the higher density of NV centers appear? Is it in diamond volume, close to the surface, or is it a random distribution?
It's really up to us how we engineer that solution. So we can grow electronic grade diamond, but then grow a small amount of high nitrogen containing material close to the surface. People have demonstrated a few nanometers of high nitrogen diamond on top of an otherwise high purity diamond. And then you can electron irradiate and anneal that sort of material and ultimately produce a thin layer of MVs throughout that small layer on top of a sample, or you can produce bulk high MV samples that I've been talking about today. So all those ranges of possibilities are able to be delivered.
And finally, do you use isotopically pure C12 and N14?
So we use, in this particular example where we're trying to push the performance of this high nitrogen material, there are still gains to be made in coherence time by using isotopically enriched carbon sources. So that's exactly what we did.
Wonderful. Well, thank you so much for that, Andrew. And please do get in touch with Andrew directly if you have further questions. Appreciate it very much. Thank you for your time.
Thank you. Goodbye.